All right, guys, our next and final speaker is Max Kuhn.
Thanks for coming. I'm here to talk about modeling in the tidyverse. So whoever asked that question earlier was not paid, probably not paid with money to ask. Oh, in stickers. Well, we'll see. There's not even some things that I can do, right, in our company. So what I want to talk to you about basically is we wanted to go through at least the plans and give you some previews of things that you can do right now with modeling using tidy packages that RStudio has generated, but also give you sort of a peek, or at least my belief as to where we're going with this, so you can get a good sense of how things are going to evolve over the next year and beyond. So what are the goals that we want to achieve by doing tidy modeling packages? Well, the first thing, which I'm not going to go into too much here because you can read it and you've probably seen it in the manifesto and other places, is to create modeling packages that sort of adhere to our tidyverse sort of tenets. Like reusing data structures, functional programming, having the design look good, keeping functions small in scope and so on. But I really want to get to a few other goals that sort of I have about these packages. I'll emphasize two of the remaining three here. I'll talk about encouraging empirical validation and really focusing on better modeling methodology. So I have a slide or two, I'll talk about what that means. Another thing that if you've used Carrot or any of the other packages I have, you've heard me talk about how diverse the interfaces are in R for modeling packages. And so I'll talk a little bit for a slide or two about how we can maybe smooth out all those different interfaces across different packages and so on. And then I'm not really going to get into this too much, but really, especially compared to things I've done in the past, I really want these modeling packages to enable you to do basically whatever you want, right? So in the past, I've mostly stuck to machine learning models like classification and regression, but I'm always asked, like, well, how can we work with time series data in the old framework you have, or survival analysis models? And these are things that I've done a lot of in the past, and I've always felt a little bit guilty that I've sort of bypassed them in previous work. So the goal is to enable a wider range of methodologies in terms of models, but also sort of promote this idea of better, what we would call feature engineering, is thinking a lot more and doing a lot more with the type of predictors and things that you put in your model, because that's a lot of times really where performance of your model increases. It's not necessarily like, did I use random forest versus a support vector machine. That very often is immaterial if you haven't really crafted the predictors that are going to model well. Okay, so we really want to enable that with the packages that we have. Up in the corner, you can sort of see the hex stickers. It's all about the stickers. For the methodologies we have so far, there's David Robinson's Broom, and then we have some packages. Recipes does a lot of work with your features, your predictors. It sort of is designed to sort of replace what the model matrix does. There's some things about that I don't particularly like, but it enables you to do a wider, much wider variety of things with your data that you put into your model before it goes into the model. There's RSample, which really is the infrastructure for resampling, like bootstrapping, cross-validation. If you have time series, there's ways to resample time series and so on. That's what RSample does. Tidy posterior is a package I'll show you some output of in a minute, but basically it's about how do we evaluate, are there better ways of evaluating models? If we have models and we're trying to choose between them, are there, there's good and bad ways of doing that, and this is a little bit, it's not cutting edge, but it's something that's sort of different than what we are normally thinking about when we compare models. And then Yardstick, the last one on the red, is basically a tidy package that allows you to compute performance measures for your models. So whether you want to compute the area under the RC curve or root mean squared error, it's all the basic infrastructure for that. So, before joining RStudio, I always had jobs doing data analysis for a lot of clients in pharma and in biotech and things like that. And, we did a lot of data analysis, but we also were very often asked to review other people's data analysis. And, very often people did things well, but if they weren't really trained in data analysis or didn't really have a head for it, you would see what I would normally call, like, enhanced interrogation techniques on their data, like make it confess, And what usually happens is people don't necessarily realize that they're doing that or doing some sort of poor methodology, because the way that we traditionally evaluate models is it doesn't really measure the type of things that would tell you that you're doing something maybe poorly with your data. So I don't know if there's any fans of like classical stepwise regression here, but that's the example that we typically use. I was talking to somebody about this, and they said, I can't find a paper anywhere that says that that's a good idea. Like, it's in all sorts of software, and everybody does it, and people were taught it in graduate school and things like that, but nobody believes it, right? And so it's my belief that if we have better empirical validation, especially like cross-validation, resampling, we would get results back that says, yeah, you're really not doing good with this thing. And the current way we typically evaluate those models, so it doesn't have the opportunity to tell you did something wrong because it doesn't measure model performance in the right way. And what I mean by that is very often we just end up repredicting the same data set we used to model the data with, and almost by definition, it's a self-fulfilling prophecy that you're going to do better. So what I want to show you, well, before I get there, another aspect of this is, when you're doing modeling, so if you have a job doing this, your boss doesn't come to you and say, maximize accuracy very often. They probably come and say, hey, we need a model that shows if we try this one thing that we've been doing with the customers in our database, are we going to get a return on investment, right? So put it in dollars, or put it, if you work in medicine, put it in terms of mortality and things like that. So very often, we want to try to promote like loss functions, way to measure the performance of your model in terms of a relevant measure. And you can't really do that in base R functions. You can't do that in carrot right now. And so recipes and all the things that I've been working on are sort of allowing you to enable yourself to measure things that, like, let's say your boss would care about. Because if you go to your boss and say, man, that model's awesome, the area under the RC curve is 0.97, right? He's going to maybe he or she is going to look at you funny and be like, oh, good for you. Something else I'll get to in just a second, and it's sort of, I was really interested to talk to Dot Cook after her talk because she talked about the idea of practical significance. And I want to show you an example, at least what I believe, of when you can have something, your model tell you, the classical methods tell you that you're doing something great and that your predictors are really important and things like that, but when you really look at are they practically significant, you might get a different answer. So it's a difference between statistical significance and is that a big deal? Right? Which is kind of a non-technical question, but I want to find a way and give you a framework to make that a technical question, a technical way to answer the problem. So basically, don't necessarily rely on p-values for everything is what I want to get at. And the way to do that, at least the way I've come up with in Tiny Posterior, is I based it on a couple papers that I've read, and I don't really take the methodology that they take, but it sort of adopt the spirit of that. So imagine you have a linear regression model. So let's say empty cars, because like we most all have used empty cars. That data set in R. And we're trying to predict the miles per gallon of cars based on their characteristics, like the engine displacement or the fuel type it needs and things like that. So, so you fit a linear model, like linear regression, just ordinary linear regression. Very often what we would do to evaluate are those predictors in my model important is we do like the standard ANOVA F test and get a p-value from that. But what that's really doing is it's doing like what we call a nested model statistic. So it fits the entire model with all the predictors, and then it calculates statistics as if I took this one predictor out, what would the change in, would I have a statistically significant change in my like sums of squared error, and is that change large enough for me to think it's a big deal? Which sounds sensible, right? I mean, if I remove this important predictor, my performance should go down, and if the variable wasn't important, it should kind of stay the same. But the problem with that is it measures that by the p-value. And the p-value is essentially saying, hey, from an indirect way of looking at probability, is there any difference in the model with and without this predictor? And it's kind of a very low bar. Because we typically don't want to know, is there any difference in something? We want to know, is it different enough? And the p-value doesn't tell you that. It doesn't tell you anything about the magnitude of the difference or the uncertainty around that difference and so on. So I have a sort of an extended version of MT cars that has more recent data in it. And if you take the engine displacement or the fuel type or the transmission type and do the standard F statistic on them, I don't know if you can read that, but the p-values are like e to the minus 70, 170 something, right? They're all like 0, basically. So it's telling you these predictors are really important. They're statistically really significant and relevant to your model. But I kind of disagree because we haven't phrased that in terms of like, what would really happen if they weren't in the model, right? Give me an answer that I can kind of interpret. So what you can do instead, and this is what Tiny Posterior does, is if you take the model that has all the predictors, and then take another model and leave everything in it except for engine displacement, and then take a third model that doesn't have fuel type and a fourth model that doesn't have transmission, and do tenfold cross-validation on those. Okay, so you're resampling the data. And if you've never heard of resampling, basically it's a way to use, in this case, you'd use 10 smaller, slightly different variations of your data set, and let's say they contain 90%, some variation of 90% of the original data. You'd build a model on that and predict the 10% that was not in the model. And you sort of do that round robin across the 10 groups that you've artificially made. And in each case, you can get sort of holdout predictions on, let's say, what your root mean square is, or what your mean absolute error is, or R squared, or whatever you want. So for these 4 models I have 10 different estimates of what their performance is. So what I can do is I can use sort of a meta model where the thing I'm going to model in that sort of meta Bayesian model is not the actual individual data points like miles per gallon, it's the actual, let's say, the mean absolute error estimates that I get across those 10 models. So what we can do is we can fit like a Bayesian ANOVA model, and the results from that model would be what is the true probability distribution of, let's say, the mean absolute error, and that's what the histograms are. So what the density plots that we're seeing there are is, for example, for engine displacement, I think the top of that density plot tells me sort of the average loss of performance by removing that predictor from the model is about, I think it's about 0.25 miles per gallon, which isn't probably a lot, right? And then if you look at fuel type, it's even smaller than that. It's much, much closer to 0. So those density plots give you a sense of what's the probability distribution of loss of performance when I take that particular variable out of the model. And all the p-values from this are 0. You can see the one on the bottom, which is transmission type, has the biggest loss of performance when you take it out of the model. So even though all their p-values are very, very close to 0, we can actually quantify in units that we probably care about more than p-value units to get estimates of what that probability distribution is, what the loss is. So there are some Bayesian people who have this idea of what they call a ROPE estimate, and ROPE stands for Region of Practical Equivalence. And what they do is they do something more traditionally statistics. They say, okay, before you start modeling or look at your data, what do you think a good effect size is? So if I were to say, if I had 2 models, how different in terms of miles per gallon would they need to be for me to think they're really, really different? So you can specify that up front. So let's say you think that about a 0.5 mile per gallon difference is a real difference before you start modeling. So what you can do is you can show that on these plots, and that's what the dotted blue lines are. So you might have things that are statistically significant because their effect is greater than 0, but you might be able to calculate the probability that they're practically equivalent, and that's what tidy posterior does. So in the first case on the top, you would say that even though it's statistically significant, using the 0.5, a half mile per gallon yardstick or metric, I really don't think that has any real effect on my model, right? And the one below it is pretty much the same thing, right? Okay, yeah, it's different than 0, but it's not a big enough difference for me to really care about. It doesn't affect performance really at all. But the one on the bottom shows the sort of the counter argument, like a positive control here, that when you move that from the model, you would get like a 2.5 loss performance in miles per gallon units. And so what we're doing here is we're doing a more fancy modeling, but we're able to relay the things that we use to evaluate these models in the units that we care about and make direct sort of statements about the actual performance of the model that a p-value doesn't really give us. Okay? It's much more complicated, and it's not, it's not like bleeding edge or anything like that. All the machinery is around, and it's pretty easy to do. It's just that we tend not to try to think of models and anything but p-values because that's what SAS or base R and all that gives us. So we want to give you tools that you have to look at and understand, but it can give you more informed ideas about how well you're doing when you model. So if you did stepwise, classical stepwise, and you cross-validate that model and look at the performance of that model, you're much, much more likely to get more, in the technical sense, like honest estimates of performance from that as you would get from the standard output that just gives you your F statistic back using the exact same data that you've tortured as you've done stepwise regression. So that's the whole idea behind, in these packages, sort of enabling empirical validation so we have good methodology. So another big thing I'm working on right now is sort of smoothing out all the interfaces. And if you see my presentations, this is not new, but on the left-hand side is just sort of like a list of, if you have a variety of different machine learning models or classification models, and you want to get the class probabilities for a set of new data, you have to remember all this minutia. So you have to remember it's this or that, depending on what package I use. Even for packages that do the same model, the syntax can often be pretty different. And so what Carrot kind of fixes this, but it fixes this from the machine learning model standpoint. And my goal is to sort of like fix it like for good now, using some different technical approaches. So I want to do this for survival models or repeated measure models and so on. We also want to sort of like extrapolate out beyond making the interfaces more smoothly. What we want to think about is, let's define a model without thinking about what the package is that's going to fit that model. So let's say I want to fit a random forest model. What I'm working on now is we can write just a simple specification of what we want for a random forest model, and later on say whether we want to fit that with R or with Spark or HTO or whatever sort of computational engine that we want to use. So tomorrow JD is going to talk about, spoiler alert, put your fingers in your ear, but he's going to talk about TensorFlow and using that from R to do the calculations using Python and TensorFlow. And so we can do that for a lot of other cases. You don't have to fit your models in R. There's plenty of instances inside of R where we give the computations to C or to Java to do them. So I want to abstract that out too, that you have the choice to use R or something else. So you wouldn't have to worry about the syntactical minutiae you see on the left there, and also necessarily where you're going to fit the model. So that's one aspect. So I'm working on something that I'm currently terming a pipeline, because that's the best word I can think of it. Naming things is hard. And the minimum thing you would need for like a modeling pipeline is a specification of like what variables are in the model, and whether they're predictors, a strata, or random effects, or whatever role they play. And then a declaration of what exact model you want to use in terms of, am I fitting a mixed model or a Cox pH model and things like that. So that's a minimum, but to build better models and encourage feature engineering and things like that, we want to create a system where we can layer in other aspects of the model that you may or may not want to use. So for example, if you want to do some preprocessing methods, like do PCA on your data because they're highly correlated, or if you have some categorical predictors in your data set that some of them only occur at like a 1% rate, you might want to dump those into an other category, some things like that. So, optionally, you might want to specify pre-processing methods that'll give you the ability to do that. And right now, you can do that in recipes. You might also want to layer in things like some real simple feature selection opportunities where you can pre-screen your variables before they go in the model. So we can have a specification where you can say, okay, here's the type of filter I want to do, and add that to sort of the modeling pipeline. And then, you might want to calibrate your probabilities if you have like a big class imbalance and things like that. So, there's a list of like, the minimum things you need to do to fit the model, but let's enable you to do some other things that might really improve the quality of what you generate. And so on the right-hand side there, the top part is basically a recipe that would specify, hey, I want to model in this data set I have. The response is a function of all the other parameters, but I have some missing data, and I need to think about the modeling function doesn't like that, so I need to do some imputations. Let's do like k-nearest neighbor imputation to fill in the missing predictor values. Well, you might not know what the value of k you should use is, so you might want to try different things and do a little bit of model tuning. So what we would do here is we would enable you to say, hey, I want to change k, but I'm not really sure what its value is, or I'm going to try multiple values. So you can give it sort of a placeholder function that right now we're just calling varying. It varies. And it sort of leaves that as a placeholder for, we're going to do something here, but I'm not exactly sure what the values are just yet. And then you can create a model specification. So if you're fitting a random forest, you don't have to say whether you're using Ranger or random forest or what have you. You can just say, hey, I want to fit these many trees, but I also want to tune over the number of data points, the minimum number of data points to make a split in the mtry parameters. You can also lay down placeholders there. You can, again, if you were fitting a different model, like a parametric survival model, maybe you want to see how that model works over different distributions. Maybe it's log normal or Weibull or what have you. So, we can sort of lay the groundwork for, let's define what we want to do and not really do it yet, but put placeholders for the things that we want to just come back to and evaluate because we're not sure what the results are. And on the bottom there, we would just create like a pipeline object very much like you would create like a ggplot, or if you use recipes, an initial recipe. We just keep layering in these things that we want to do because it's a modeling process, which includes feature selection or how we manipulate our predictors and so on. And all the pipeline does, and all we've done so far is say, here's what we're going to do. And so then we have our data and we eventually want to do it, okay? So we take our model specification, and if we knew all the things that we wanted to do, if there were no varying parameters there, we can just put that in a fit function and tell it what engine to use, whether you want to use Stan for the mixed model or LME or LME4 and so on, and just have it go do the fit like it normally was. And we take care of what that model fitting expression is under the hood, so you don't have to worry about, well, wait, what is it in Stan versus and LME? You don't have to necessarily think or worry about those differences. But if you do have those varying parameters, what you can do is you can do things like grid search or some sort of optimization to try different values of those parameters, maybe cross-validate those selections, and then tune your model over, let's say, the number of neighbors in your imputation or the random forest parameters. And since we have those in the pipeline can detect exactly what variables you want to change. And it's not very prescriptive about which ones you can and can't change. You can put them right now for any of them. And then you can use some code that will, I've basically got it pretty much worked out. If you want to do random search, you would just generate however many random parameter values of those varying functions that you want to evaluate. And then you can have an update function that after you pick the best one, will update the model specification, say, oh yeah, it should be 7 neighbors, or it should be a Weibull distribution based on my resampling statistics. And then you can fit your final model. Okay, so what's going to happen is after we lay the groundwork with some of this model specification stuff, there'll be a variety of somewhat small in scope packages that do grid search, or do things like model calibration, or a little bit of feature selection. Or let's say you want to do something fancy like a genetic algorithm to optimize these models. We'll have packages that are, again, with the tidyverse having small in scope packages to do these different components. The hardest part right now is the model specification, because even though I've sort of done that before for Carrot, it's kind of crazy now that I'm thinking about exactly what I want to do. So that's kind of where things are at right now. And so at least for the next year, that's going to be what's on the board for modeling in the tidyverse. But there's plenty more to do besides this. So you can always send me emails if there's something I'm not thinking of here that you think would be a good idea. This basically gets that. The only thing I want to emphasize here is, people like Carrot because you can get very quickly to a good performant model without having to write a lot of syntax. And it does that by doing a lot of things for you. It's probably, I'd risk saying this, but it's like the most untidy package on CRAN. It's like, we have functions with like 17 options, but that's not good from a programming standpoint. But a lot of people like it because it makes a lot of choices for them, and it lets them not have to worry about writing 20 lines of code. So the goal here for the tidy modeling is to have small in scope packages and functions. And if you want to sort of roll your own, we'll have plenty of examples in code to do that. But we will have higher level APIs like we have with Carrot. So if you want to say I don't really know anything about partial least squares, but I know if I do this, I'll probably get a good model by doing that. Okay, so we'll have both the higher and lower level APIs that do that. Okay? And thanks everybody here. Hadley in our group who are excellent. David Robinson for Broom, which is a great package. And anybody who's ever submitted a PR or a bug request, I really want to take a minute and thank everybody for doing that.
Thanks. Hi. So I'm just curious, would this replace Carrot in some way in the future, or?
Everybody always asks me that. No, Carrot's not going anywhere. I'm developing that just as much. It's 13 years old almost, right? So I'm not doing a ton of really big fundamental developments to it, but the rate I've been going for the last 2 or 3 years hasn't slowed down. So that's always going to be a thing. I'll be pushing the envelope more here. So when people say how can I do time series in Carrot, I basically say, well, come over here and look at R sample and the stuff that I'm doing. It's not frozen, feature complete, but for more invasive changes I would have to make to Carrot, I'd rather just do them here.
Oh, you didn't throw the microphone at me. Can you tell us what you're thinking about model visualization?
Model visualization. I haven't. I mean, I've always thought about that, but I haven't thought of anything from the standpoint of these modeling packages. I mean, there will be, again, like top-level functions. If you've resampled your model and you just want to get the observed by predicted plots, yeah, we'll have functions for that. But I think that I want to get through this first. I want to have models to visualize before I think about that, yeah. All right, thanks for coming. If you have any other questions, just come by and find me and let me know.